on this computer. All right, and what I had said a few minutes ago, I don't know if we'll get to it yet today, but if you want to get ready for where we're going with the programming stuff, I already have a link for it up on Blackboard, but it's this program called Dr. Racket. So if you go to racket-lang.org and download the latest version 8.2 for your platform, you'll have what you need for the class. Okay. Now let's go over here. All right, so the usual homework is Bible homework's 10%. There'll be 3 medium-sized assignments that are due by the end of the semester. Pace yourself. Homework assignments are half your grade. There'll be lots of those. 2 exams, midterm and a final. I have my usual policy. If you do better on the final exam than you did in the midterm, I'll replace your midterm exam score with whatever you did on the final. But they're worth 20% each, 40% of your grade. So the same grading scale as I use in all my classes. All right, so now we want to start talking about the concept of a programming language. What are we trying to accomplish? So again, you know, in this class, rather than focusing on writing programs to solve algorithms, business problems, and things like that, the algorithms that we're going to be trying to solve are the constructs that support a programming language that allow somebody to write programs. So starting point is, what is a programming language? It's this conduit between us and this computer so we can tell the computer what to do. All right, so we're going to be trying to write a tool that allows us to tell a computer what to do. You go back, you've seen this slide in every single one of my classes, right? How do human beings solve problems? Remember stuff, we ask questions, repetition. Every single programming language that exists will have facilities for these 3 things because they are attempting to mimic the way human beings solve problems and give us the necessary constructs to tell a computer what to do. All right. So like we talked about in the very first programming class, 200, if you're looking at something that doesn't have 1 or more of these, it's not a programming language. That doesn't mean it's bad. That doesn't mean it's not a viable tool. It's just not a programming language. So the joke there is always, you know, when you ask who has had, you know, what programming languages you've had, the de facto first answer is almost always HTML. HTML is not a programming language. It's a data representation language. Nothing wrong with it. Doesn't mean it's the last kid picked for kickball, but not a programming language. All right, so our target in here is going to be building a tool that provides, at the very least, these 3 facilities. A way of representing variables. So we're going to have a whole section on the variable environment. Where does that stuff get stored? How does it get resolved, right? We think about, you know, when we first started learning about variables, we started talking about variable scope. In programming classes, we say something along the lines of all variables resolve to their most local definition, right? You know, you might have 5 variables all named A, right? And when you're using A in line and you go to resolve the value of A, it's bound to the most local definition of A. So even if you have it defined way up top, if you have a local variable inside the function you're currently in for A, that's what the current use of A is bound to. All right. So one of the things we'll have to deal with is, how do we actually implement the concept of scope so that when we resolve a variable, it gets resolved to the correct binding for that variable, because it is allowed in a computer program to have more than 1 variable with the same name bound to different values. But depending on where we're actually referencing that variable, we expect a certain value. That value should be predictable, right? We don't want it to roll the dice and just give us one of the values of A. It should give us the correct value of A relative to where our line of code was. It should be the most local definition. So we'll be talking about variable environments. All right. So kind of an interesting concept there is, what I just described sounds like it could be somewhat complex, right? When we really think about variables as being, they're kind of these throwaway things, right? Like, you just say int a equals 5 and you got a variable, no problem. That's what the end result is of the programming language. But behind the scenes, that programming language is having to do some heavy lifting to manage a variable environment. So we'll be looking at some different implementations of that. We'll start off with kind of a simple implementation of it. And then we'll see some of the shortcomings of that. Similarly, asking questions. So typically we think about like an if statement or something like that. Well, those are reliant on having the idea of a Boolean expression. What's a Boolean expression? Any expression that boils down to a single value of true or false, right? Our old mantra from 200. So now we'll have to implement the concept of Booleans true or false. That has to mean something in our language. We have to have a way of representing that in our language. You go back to one of these older programming languages like C, and Booleans were represented as zeros and ones. They used the numeric literals to represent Booleans, which means that when you implemented the less than operator, the thing that we use, the less than operator, where if you go back to some older languages, sometimes the less than operator might be like an LT. So we get to choose what our less than operator is as the language designer, right? We get to, we can just make it like a comma or something like that. That kind of doesn't make great logical sense, but it's technically allowed, right? If we're the ones inventing the language, we can use all sorts of symbols for different things. But, maybe we have an older language that we decide that the less than operator is the 2-character sequence LT. Well, now we need to define behind the scenes, what does it mean for the left operand to be less than the right operand? We're the ones implementing that. We have to decide what that means. Make sense? Okay, so we'll also implement the equivalence operator and all sorts of stuff like that. Again, things that we think as being very, very, very simple in terms of, oh, this is kind of like throwaway stuff in a programming language. How hard could that be? We're going to think about, if we actually had to implement that, what might it mean? Now, we're not going to get down to we're going to be working with interpreters in here as opposed to compilers, mostly because if this was a compilers class, our end language that we would have would be significantly more simplistic. Because creating a compiler, remember, compilers translate a high-level language into a low-level language, is a significantly more difficult task than writing an interpreter. Interpreters are computer programs probably written in a high-level language that sit on top of an existing computer, probably an existing compiled language. So some of those things, like Boolean operators, the concept of what less than means and stuff like that, already exists. So we will be leveraging things that do already exist in Scheme. So we don't have to get down to the bit level to invent constructs. So we can focus more on the implementation of the language. So we'll use Scheme's idea of less than or greater than, that kind of stuff, to implement our version of less than or greater than, even though we might pick a different symbol. We'll probably purposely pick a different symbol than Scheme's version of less than or greater than, just so our language feels unique, right? But we'll still use that underlying concept of Scheme to write that, so that we're not going all the way down to the low level of implementing something. If we go down to assembly language, like you guys look at in the 325 class, when you look at less than and greater than and things like that, these are implemented in the assembly language through branches. You have branch if less than, branch if greater than, and that's looking at two different hardware registers, right? And making a decision where to branch in the program, where to jump, a different line of your program it should jump to if a certain thing is less than something else, that kind of thing. So at some level, down at the processor level, they built in a magic trick that ultimately understands the concept of numerical less than or greater than. And if you want to do something that's more complex than the numerical side of things, like is one string less than another string, now you have to decide what does it mean for a string to be less than another string. Does that make sense? All right, so we'll be inventing those concepts and talking through some of those concepts. Same thing with repetition, exact same thing, still using Boolean operators, but we're repeating something multiple times until some condition is met. We'll also be looking at writing functions in here. And we'll start off by writing kind of a simplified version of a function, and then we'll decide, hey, we should support recursion. Well, what does that mean? Well, when you have a recursive call, remember recursion is when a function calls itself from within itself. Well, what does that mean? If you're inside of a function that you're currently running and you need to call that function again, you need to put the current function completely on hold. That means you need to store the current state of an entire function. Well, where does that go? Well, maybe in our variable environment, that thing we invented up here. Well, that just made that thing more complex, right? Okay, so that's what we'll be dealing with in this class. The first several weeks, we'll be kind of learning this new programming language Scheme, which is actually a very simplified language, and we'll start looking at the constructs of it today, which is kind of why I use it for this class, in that the language is so small that you can really learn the constructs of the language very quickly. But it also kind of makes you solve problems in terms of you've heard me say this before, we solve problems in terms of the tools that are in our toolbox, right? Our toolbox is very small. We only have certain functions available to us in Scheme. Scheme is a type of language known as a functional language. It's a list-based language, as opposed to, I advertise Java as being like a string-based language. So Scheme, we use lists. And let me just quickly, we'll just do a quick, I thought I started Racket. Ninja. All right. And this will be later on in the slides as well, I'm sure, but I'll introduce it earlier. First thing I'll go ahead and do, because you'll want this for your doing the assignments. When you go up to the version that says language, and say choose language, it's going to give you some languages to choose from. Of course, you want to choose one of these German ones. I think the one that you'll like the best, I think the default is advanced student. If you switch to intermediate, no, you know what, leave it as advanced student. It's already set to where it should be. If it's set as something else, just choose it to advanced student. All right. So we think about, I'll just do the high level thing here with Scheme, and we'll see this through examples. But first thing we want to be able to do is create variables, right? Okay. In Scheme, I said everything is list based. So that means in Scheme, everything will look like this initially. You have an empty list. Inside of a list, we're going to have our function name followed by params. We're calling a function. Okay. So I'm going to go ahead and I'm going to call the define function. We'll define LST to be, let's just put it the list 1, 2, 3. Okay. Now, the way this works in Scheme is you can just completely use the interpreter real time down here if you want. You can do a define list, 1, 2, 3, all that stuff. But as soon as you run whatever program you've written up here, anything that was in memory down here disappears. So typically what you'll do is you'll write your programs up here, and then to test them, you'll say run. All right. So if I go ahead and run this guy, program is now run. I've defined a variable named LST, and I've set it equal to the list 1, 2, 3. So down here, if I type in LST, I'm asking it to resolve the variable LST, and there's my list. All right, so we'll just go ahead and add it to our slides here, even though it's probably in Scheme functions. So we have define. This creates a variable. Yeah, but all right. Then the famous two functions from Lisp. You may have heard of these before. We have a function called car and a function called cdr. Have you heard of these before? In like some sort of joke or song in a t-shirt or something like that. These are list-based functions. Car returns the first element of a list. And it's important to focus on that thing called element, because lists can contain elements that are anything that is a Scheme data type, including other lists, including functions. All right. Almost everything in Scheme is what's called a first class variable. Okay? It exists in its current elemental state, whatever that is. It just so happens, my simple example here, I have 3 elements, and all 3 of these elements are integer literals. Pretty simple list, but nothing prevented me from having the list containing 1 as my first element, or even something scarier than that. But we'll keep it relatively simple. So car returns the first element of a list. So if I come down here, I haven't rerun the program, so it's not broken or anything, and I say the car of LST, this is going to give me the first element of that list, which is the 1. Now, right now, you should be thinking, you probably are thinking, like, okay, how useful is that? Right? You'll see. All right. So that's one of our functions. Next one, cdr returns the rest of the list, not including the first element, as a list. Next important piece there is that cdr always returns a list. So cdr returns the rest of the list, the thing that you would get after the car, gives you the rest of it as a list. So in this case, the cdr of LST, now first of all, car of LST does not change LST. This is a function. The function is called car. You pass it a single parameter, which is a list, and it boils down to the first element of that list. But it does not modify LST. If I go and type in LST here, it'll still be the list 1, 2, 3. LST has not changed. Okay. In fact, that concept there of how do I update the value of a variable is going to frustrate you until probably after the midterm, because we're not going to look at how do you change the value of a variable. Variables aren't as variable as you want them to be in Scheme. All right, so that means whenever you need to change something, you're going to have to do it through local variable environments, something we're going to be introducing called a let, but there's multiple versions of lets. We have a let star, we have a let rec, all sorts of different lets, and that allows us to create a little local environment. That also, by the way, makes it difficult to change the value of a variable. So then how can we accomplish changing the value of a variable? Maybe with a recursive call where we pass in a new version of that variable as a parameter to the same function. When you're done with this class, you'll only be able to think about things recursively. Going back to iterative mentalities will be kind of difficult. All right, which will be a good thing because then you'll kind of balance out. It's kind of like riding a bike. And then recursion won't be all that difficult anymore. All right, so we saw that car did not modify our list. If I do the cdr of LST, we expect it to give me the rest of the list, not including the first element, as a list. So this should give me the list 2, 3. Make sense? All right, now I can take the cdr of the cdr of LST. What do we expect that to give us? Just the 3, because this first cdr of LST is going to give us the list 2, 3, and then the cdr of that is going to give us the list containing 3. It is well, it's going to show it as a list, yeah, because cdr always returns the list. So there's the list 3. All right. What about the cdr of the cdr of the cdr of LST? By the way, you're going to hate parentheses when this is all done. You already do? Oh, it gets so much worse than this. All right, so this is going to give us the empty list. Our mentality in here should be to kind of think of the empty list in a similar light as we thought about the empty string in Java. Empty lists become kind of our baseline pattern that we can build lists on top of. That makes sense? Hold on, I need some coffee. Somebody yelled? Oh, somebody was trying to enter. I see what you're saying. Did they get it or they bail? Unimportant. Do we see what name it was? Matt? Oh, and by the way, any of you in here, you can also join the Zoom channel if you want, if that makes it easier to see the screen. Just make sure you turn your mic off so we're not getting crazy feedback. And those of you who are online, I typically don't see the chat thing. That's Emily's job, to yell at me. Hey, look, that's just the way it goes. To yell at me if there's chat, but the better solution is just to scream out if you have a question. I won't be offended. I might make fun of you, but I won't be offended. All right, so I put too much creamer in this, I think. It still tastes pretty good. But this was actually this was my morning workout, was filling this because I had to sit there and hold it. It didn't quite fit underneath my coffee maker in the office. First world problems. So I'm gonna. This one doesn't quite work that way, but I'm going to 3D print something that will go off of it and hold it at an angle. Well, I say I'm going to 3D print something. I'm going to have Blade design something and then 3D print it. We hired him, you know. Blade is now Professor Blade. He's assistant professor in the department, working on his PhD. Teaching 150, and then whenever I want him to run a lab, he'll run labs in my classes. I mean, I got tea times. Well, there's priorities here, people. Right, exactly. It's like Puppet Master. That's one percenters. Right now, his job is we're beta testing some, he's created multiple designs for some 3D printed stuff for my boat. Well, but we have it in a slip down in Milwaukee River downtown. So we only tow it when we have to take it away from there. Although we had somebody towed it themselves the other day. took it and they didn't put the Bimini top down, and that thing ripped off. It's the whole top of the thing ripped off and flew down the highway. Oh, a lady hit it on the interstate. Yeah, $21,000 in damage. I'm gonna be without it for a month. But I got a really nice loaner. I'm driving my wife's one-size-fits-all Honda Fit. I want you to use your imagination. 6'5", 400 pounds in a Honda Fit. Actually, it should be a commercial for the Honda Fit because I shockingly fit in there pretty well. You know, when I put it on kind of like a sweater. And then once I'm in, once I'm in. The bad thing is I didn't even have autopilot on the Tesla because I just turned it off because I was getting ready to take my exit on I was on 94, and I bet you if I had it still on, I wouldn't have gotten hit. I think the car would have avoided it. Well, yeah, but also kind of an interesting, I mean, make lemonade out of lemons, right? Damage happened, nobody got hurt, car got damaged, that's done. But at least looking at it from a technical academic thing, I really think that the sensors around the car would have avoided, it's able to do things that a normal human would have trouble to do in that moment. It would have seen the car coming over from one side. It would have been able to see whether there were cars on the other side, which there wasn't, I know after the fact, but it would have been able to do a maneuver in the moment, looking all around the vehicle that maybe I wouldn't have been able to check as many things quick enough in order to come up with that solution. That doesn't mean that there won't sometimes be, sometimes it might just, I don't even know how the algorithm might work where it decides what to hit if you're gonna hit something. It's kind of like those puzzles you see on some of the online videos where you have to make the decision, do I kill the three children, or like hit the parade of old men. Yeah, that's what I'm saying. So let's say there's 30 elderly people, like all sick, marching. This is all recorded too. And some of these guys, they have a limited time left on Earth, right? And then you have 3 children. So you got like 50 people versus 3 children. Who do you hit? And that becomes an interesting thing to think through. And I mean, it's baffling for a human, right, to make those decisions. It's an impossible decision. But how would a computer discern? I mean, first of all, it's probably not going to necessarily be able to detect. Although now the car does detect 4-legged animals. Before, they were all just motorcycles. Or people. It does detect people, which is always weird when you're in the middle of the interstate and all of a sudden you see a person walking across the road. But that's kind of an interesting technological problem of how does it make decisions maybe based on emotion. I don't know what. I don't know. I don't know what the underlying. It probably has some kind of algorithm.
Right, but like you can't physically in that moment, like it has to reduce down to something where it's like there's going to be less damage.
Correct. Yeah, and I don't know how it does that, but I know that it does do that. In a situation where an accident is unavoidable, I think it makes a decision of maybe what's best.
Like this is going to have lost speed.
Yeah. Or even taking that philosophy problem a step further, choosing between you, the driver, and
someone else.
Well, yeah, I mean, let's take the 3 kids and yourself. Well, just keeping it as an extreme example, right? That makes it harder. Like from an individual perspective, do I want my car to save me or to save the strangers?
But if your car hits the strangers, then wouldn't you try to hurt it?
It's manslaughter. It's a lesser.
Yeah.
And what if the car made the decision? Like, look, I would have swerved, Your Honor. It's like, no way I would have plowed through the preschoolers out on a walk. It's like, there's like, look, there wasn't even traffic. There was no other cars involved. Why did your car deviate? It's like, well, I mean, Mr. Gonzalez was messing with wires. There was a thing. Yeah, so it's
lawsuit Tesla then.
Yeah, but they have so many lawsuits. It is interesting. I've considered that, like, some of the things that they do to kind of innovate really opens themselves up to like a substantial risk when when you're, like doing the full self-driving in town where it's, you are now dodging people on bicycles and motorcycles and just people walking and, things that are, like the interstate, even though you're going faster, is an easier problem to solve. It's a lot more controlled. You almost ask yourself, like, why risk it? Why be that company that's kind of leading in that space when you're just asking for problems, right? Legal problems, lawsuits, things like that. I don't know. It's kind of a fascinating thing. But in any case, nobody got hurt in my accident. The other lady was able to drive away in her older SUV, whatever it was, and of course, an expensive car just falls apart. Right, it was like made of paper, so it was not drivable. The wheels were like off. I had just gotten new tires the day before too. So earlier that week, I got a flat tire, which I hadn't had a flat tire maybe ever in a car. So I took it in, and apparently it was a nail, and it was in the sidewall, so you can't fix that. Well, then I find out that the tires that came on the Tesla are like racetrack tires. They're not made for like winter, which is kind of interesting because I drove it off a lot in Chicago during a blizzard. They sold me that car and had me drive it away in unsafe conditions, apparently. So I had to buy 4 tires. It just so happens Tesla's tire sizes are different, of course, right? So I had like 2 choices of all-weather tires, like expensive and really expensive. So I got all brand new tires, and less than 24 hours later, wrecked the car. But I made sure to tell the body shop, like, I want to make sure I get replacement of those same tires. Don't put the racetrack ones back on. I'm back to square one. All right. Now that we've deviated as Whitman does, let's get back to our cars and cooters. All right, so we see how you can string these functions together, because ultimately this guy right here boils down to a list, which then becomes the input for this function right here, which boils down to a list, which then becomes the input for this function right here, which ultimately boils down to a list. And what's that final list? It's the empty list. Now, what if I tried to do the cooter of the cooter of the cooter of LST? If you try to take the cooter of the empty list, it's going to give you an error because it says, look, you have to have at least one element in a list in order for me to take the cooter of it. What if I try to take the car of the empty list? It says you need to have at least one element in the list in order for me to give you the car of that list. So the next thing that should pop into our head is, well, we probably then need to have some sort of way of asking if a list is empty. We have these things called predicates. Predicates are functions that take a single parameter and return true or false. And we'll have several predicates we'll look at in here. Not that many. Several is a pretty appropriate term because, like I mentioned before, Scheme is a small language. Okay, but one of the predicates is the null predicate. And a lot of times we can identify predicates in the wild because they end in a little question marky thing. That doesn't mean when we write our own predicates, we have to have the question marky thing. This is kind of like that naming convention, like when we historically we've looked at a is this a class method or an instance method, and we see the first word, if it starts with a capital letter, we're kind of confident that that's probably the name of a class because it starts with a capital letter, not because Java or C++ requires it to start with a capital letter. That just happens to be a common convention among programmers. All right. So built-in predicates typically have a question mark at the end of them, which then probably should follow that if we write our own predicates, maybe we put a question mark at the end of it just to follow that naming convention. All right. So null returns true if the param is the empty list, and false otherwise. So null LST is false. Just remember, LST has 3 elements in it. It is not the empty list. So you could think of the null predicate as kind of saying, is this the empty list? Null cdr of the cdr of the cdr of LST is true. Cdr of the cdr of the cdr returns the empty list. Okay, so now at this point, you might be thinking, okay, I'm kind of following what you're doing, but how useful is any of this crap? We're not necessarily seeing how we might use this yet to solve real problems. We're going to be using this language to write a programming language. And there'll be cars and cdrs all over the place. Oh, in parentheses, so many parentheses. So many parentheses. Okay, now you really want to freak out here? You've already seen it. You can do the car, the cdr. Oh, this is a big one. The car of the cdr of the cdr of LST. That'll give us the car of the cdr cdr. Cdr cdr was the list 3. The car of that is 3. And of course, you can do the cdr of. Now, it's very important that you pronounce those correctly, because we have the cadadders, we have the cdrs. Now, I refer to this kind of stuff as syntactic sugar. This is the car of the cdr cdr. That's what that guy boils down to. But now this only goes so far. I think it maybe lets you string like maybe 6 letters together before it starts being a problem. I would not make it a habit of using these unless it's like very obvious. Like for instance, the cadder might be a common one. The car of the cdr. That could be something like, yeah, that I'm safe using that. But for a while, I would spell it out. I want the car of the cdr cdr. You actually write those functions with the extra parentheses and that kind of stuff. This is just shorthand, syntactic sugar for meaning the same thing. And at some point, your brain gets stuck and you won't be able to follow it very well anymore. And then you're also at the limitation of the interpreter and what it allows. All right. So any more than 3, I would say you're kind of playing with fire. All right. So questions about cars and cdrs. Car gives us the first element. Cdr gives us the rest. Null is a Boolean, is a predicate, a Boolean operator for determining whether something is the empty list. All right. Let's just keep going with the programming stuff. All right, so that gives us, and then we've seen define, although we'll actually only use defines in here for a while for defining functions. So conditionals. We're actually going to be looking at multiple types of conditionals here. We're going to have if statements. We'll just call it the if function. And then we'll also have the cond function. If allows us to ask a single question and respond based on true or false. Syntax is if, Boolean expression, true expression, false expression. So if this Boolean expression boils down to true, do whatever this guy says to do. Otherwise, do whatever this guy says to do. It's your usual if else, just in list format. So I could say something like if, actually, let's write it up here. If null LST will boil down to the empty list. Otherwise, let's boil down to the catter of list. Actually, let's do the car of the list. So this is asking if list is the empty list, if that's true, boil down to the empty list. And we can either hard code the empty list in there, or we could just say boil down the list, which would be the empty list. Otherwise, give me the car of list. That's what that if statement says. Now, list is currently the list 1, 2, 3. Is 1, 2, 3 the empty list? No. So this is going to give me the car of LST, which is 1, as an element. So car returns whatever the first element is. Whatever kind of animal that is, could be a list, could be whatever, but it returns whatever that is. Go ahead. It's called, it's quoted. So this guy right here says, don't treat this one as the name of a function. Since everything's a list, the first element of a list by default is considered to be the name of the function. So if I remove that from there, it's going to try to store in list the function 1 applied to the parameters 2 and 3. That make sense? So by putting the quote in front of it, I'm saying, look, this is the literal value. I want the literal list 1, 2, 3, not the result of the function 1 being applied to the parameters 2 and 3. All right, so there's the car of our list because of this guy. If instead I say, if null, the CDD, so of list, which is the catter of this is the list 2, 3, the catter of that is the list 3, the catter of that is the empty list. So is this guy the empty list? Yes, it is. So boil down to that value, which is the empty list. Oh, it won't be it'll boil down to LST here, which isn't the empty list. It's the value of LST, which is 1, 2, 3. So if I wanted to show the empty list, I would have to either write that, or I could write CDDR LST. And there's our empty list. The reason for that is just like we saw before, this does not modify the list LST. So even though I'm asking the question, is all of this stuff, the CDDDR of LST, is that the empty list? If yes, boil down to LST. Well, the value of LST is this guy. All right, so we get how conditionals work. All right, our other kind of conditional is something that we actually, up to this point, you probably have not commonly used, because I would say in typical high-level programming languages, it's kind of fallen out of favor, and that's something called a switch statement, where you kind of, we typically have replaced switch statements with nested if statements. Ifs with if else's, that kind of stuff, or else ifs, you know, whatever. And we effectively end up with a similar structure to switch statements, which are built into most of our languages without kind of the downfalls of switch statements. In fact, I typically don't teach switch statements in any of my classes. If you've seen it from me, it was just because we had a passing example where one showed up or something, and I explained through it. But historically, the way switch statements are implemented in high-level languages like C and C++, says we're going to switch on some Boolean expression. And depending on what the value of this Boolean expression, we either hit, you know, we have a list of possible results, right? If it's a 1, do this. If it's a 2, do this. If it's a 3, do this. But the side effect of that is, as soon as it drops into one of those and does it, you then have to put a break statement in there to jump out of this structure. Because if you don't, what it keeps doing is it just falls through the rest of the thing, hitting every single branch on the way down. All right. It ends up being a cumbersome tool to use. That one little forgetful step of forgetting to put a break in there to dive out after you've hit your match ends up, I think, causing problems. Where an if with else ifs is much more structurally sound and doesn't require you to do special, you know, get out of jail type of ninja moves. Cons in Scheme don't require that break thing. They work more like ifs with a bunch of else ifs. All right. So the syntax for cond is like a series of if/else ifs with a default, we can call this the ultimate else at the end. So syntax for this is cond. Boolean expression, val, Boolean expression, val, ... Boolean expression, val, default, val. So we can have a series of conditions where if this is true, do this. If this is true, do this. If this is true, do this. Yada, yada, yada. If this is true, do this. If we're still kicking, if we haven't fired on any of those yet, the else, the default is to just do this. All right. So I'll try to hobble a cond together here. So we'll say cond null LST, return the empty list, null Cooter LST will return a 1. Null CDR LST return a 2. I say return. I'm boiling down to a 2. This isn't actually returning it like it's a function. The entire result of this function call will boil down to a single value that is a 2 or a 1 or the empty list. Null CDD DR. Actually, let's not do that one. Let's just do a default at the end. Default 7. Just else? Yeah, it was just an else. I thought it was default. Even a better syntax. It says what it means. All right, so first thing we asked is LST null? It's not, so we don't do this. Is the cooter of LST null? It's not, so we don't do this. Is the cooter of LST null? It's not, so we don't do this. We end up with a 7. Just modified a little bit there where we have the cooter of LST, which is null, so we'll end up with a 2 here because it did fire right there. But we didn't have to break out. Once it hit this, we were done. So this allows us to have a series of conditionals in a row to make decisions, as opposed to if we were writing this with a bunch of if else, we would have had to nest a bunch of if else's together in order to accomplish that same task. This looks a lot more, I don't know, structurally pretty or something like that. All right, questions about conditionals? So we know how to define variables now. That's a little bit useless for us at the moment because the only kinds of variables we know how to define are effectively a single variable that just gives us a starting point that we can go and do stuff with. We're kind of missing the other side of the coin where how do I update a variable? And we're not going to see that for a while because it's actually not something you're going to do very often in Scheme, because we're making recursive calls. So when something needs to change, we'll just pass the changed version of it to the next call to the function rather than update some global value. Is there a question online? I guess they unmuted for a moment to burp. All right. So questions about asking questions. Get it? Memory asking questions. Early compilers, because of the way the syntax had to be, they required you to, actually, this might not be a true statement. Just in case, I'm going to speculate. The allowable syntax in like a language like C has evolved over the years where you don't always have to use curly braces, or you can say else followed by an if, things like that. So you can kind of structure an else if in a fairly organized way, where before that, you would have actually had to nest them inside of each other, kind of causing a mess where a switch would have made more sense. I'm trying to think back to when that would have been a true statement, because curly braces have actually never been required. And that's why I harp on the idea that it's never wrong to use curly braces, but they're not, if you only have a single statement. The syntax behind the scenes for an if is if Boolean expression is true, statement. and we'll be talking about that in here, where a single statement can be a block statement, opening curly brace, closing curly brace, as much crap in there as you want, or it can be a single statement, like print hello. That's a statement in and of itself. So with that in mind, it might just be a more plausible reason is the person who wrote the initial language that had that just decided, hey, you might want to ask multiple questions and have results. So here's a structure for doing that, not necessarily paying attention to the fact that you can pull that off probably just as well with a series of if else's. It's probably I'm guessing that's the more correct answer. But ultimately, that's going to come down to the efficiency of the compiler. Because under the hood, whether you're using if else's or you're using switches, you're going to see the same assembly code. Possibly in an interpreter, there could be a speed value because you're still asking the same number of questions. Typically, the cleanest way to talk about efficiency of any program, you get into the stuff like it's an order n or an order n squared or log n, this stuff. I don't think that stuff is overly important 99.9% of the time. But when you're thinking about the efficiency of one algorithm versus another, kind of the top level, easiest way to think about them is how many questions do I have to ask to get to my result? Every question takes time. So every single time you have a Boolean expression, that takes a little bit more time. So the difference between nested if statements and a switch, I mean, you're really asking the same number of questions. So if there's a speed difference, it's not substantial. I really think it's probably most likely that whoever wrote the first language that had them both didn't really consider the full utility of an if else when they wrote it. They just kind of said, oh, you might sometimes want to ask a question that just has a either or type thing. And then sometimes you want to ask more complex questions that have a series of questions. And they didn't necessarily consider that, a viable solution to that is to use ifs that are linked together. But as we keep going down the logic path, it's possible that very early compilers were not recursively written, which meant that as they did compile your if statement, it's possible nested ifs did not work in the earliest compilers. It couldn't do that. It's like, oh, I found another if, so I need to run this a second time. That's also possible. Let's call those mostly theories, but I'm going to still guess that the answer is the one where I think the person who wrote it didn't consider that the syntax that already existed could be used for that extra utility and just said, this is something we might want to do. Kind of like in your car, you have multiple ways of increasing or decreasing the volume on a lot of cars. Do you really need that? You need the extra ways to increase the volume? I mean, you might. Do we prefer the button on the steering wheel or the knob? Which? Steering wheel? So that means you don't even need the knob. Or what if the button on the steering wheel is hidden by your 2.2 pound weighted hack for your steering wheel so you don't have to put your hands on the wheel? Yeah. Because otherwise you got to have your hand on the Tesla. What's that? You want to be like, you got to hold your iPad. Yeah, but you can't, while you're driving, it doesn't let you play games or watch HBO. It does let you watch HBO on it when you're parked charging. I did consider this after the accident. Because in a Tesla, there's no way to open your glove box manually. You know, like where my insurance and stuff is, right? You have to go through that big computer screen to open it. So what if you were in a bad enough accident, your computer went out? And now the cop wants to have your insurance card, you can't get to it. Your car is holding it hostage. Really? I don't have a wallet because my yeah, I mean I should do that. That's smart. But I kept when I got the Tesla, I kept leaving my wallet at home. Because before I had a car key and then I would have the wallet and the car keys at the same place. Now I don't have a car key. This is my car key. No, I have my license and a credit card and stuff in here. There's not room for an insurance card. I have my laminated vaccination card in here. my vaccine card tattooed on my armpit. My wife wouldn't have allowed me not to be. I'm not political, so you guys want to fight your fights, you can do it wherever. Just not in my classroom. But yeah, so I have that laminated. I do the double thickness thing, so it's like one of those really expensive baseball cards. Mm-hmm. Same thing like my credit card, like super heavy. It's like metal. Yeah, so when you throw it down, it like bounces. Like, yeah, that's not getting rejected. I don't throw it down. I hand it to Blade and have him throw it down. Just for the record, Blade and I are very close. He like comes to my house for Thanksgiving and stuff. So it's only sort of racist. Also recorded. Well, I didn't say all the stuff that was in my head. Yeah. All right. So those are our two different kinds of conditionals. Questions on those? All right. So now we'll end the class with a something scary. Lambda expressions. Okay, so as soon as you start using stuff from the Greek alphabet, things get scary, right? Huh? Yeah, seriously, you go with me. It's gonna get so much worse. Oh, your souls will be haunted. All right, so a lambda expression is an unnamed function. So what we want to think about here is in normal programming languages, what is a function? A function is a series of parameters that then have logic applied to those parameters that ultimately boils down to a result, right? Is that a reasonable enough definition that covers the functionality of a function? I think you're allowed to use those two words next to each other. Fair enough? You have a parameter list and then logic that applies to that parameter list. A function can exist without a name. When do we associate a name with a value? Whenever we want to use it more than once, right? Same rules as we apply to any sort of variable. When do you put a normal value into a variable? Forget about functions for a second. When do we put a normal value into a variable? If we're going to use it more than once. If we're only going to use it one time, We don't need to store it anywhere. We can just use it right away. We can either hard code it in there, or let's say we're reading something in from the user. We ask the user, what's your age? Okay. Well, we can just say, we just pass the age, whatever the user reads in, we'll pass it in directly to whatever logic we're using it, going to use it with. We don't need to store it in a variable if we're not going to use it more than once. That's realistic, correct? So is the same true with functions? We might say that it's unlikely that we have functions that we only use once, but not impossible. In fact, we're going to see in here that it's somewhat common, but we can say that it is possible that we might have the existence of a function that we only want to happen one time. Therefore, we might choose not to have it associated with a variable name, hence an unnamed function is what a lambda is. So this is lambda param list logic. All right, so we'll pick up here on, what's today, Tuesday? We'll pick up here on Thursday and finish looking at lambdas, and then start getting into some of our practice. Your first several assignments will be solving like little algorithmic puzzles that get increasingly difficult in practicing with the language. All right, questions, comments, concerns, bribes? All right, I'm heading down to chapel, plenty of room in the front row. And I will upload the recording. There's already a link on the Blackboard for the recordings.